Howdy. This video is on Gibbs free energy. The change in Gibbs free energy is directly related to the change in entropy of the universe and can be calculated from properties of the system. Gibbs free energy is also a form of chemical potential energy. Using the change in Gibbs free energy, we can determine if a process will occur. We can determine if it's spontaneous or non-spontaneous. And please remember, spontaneous in this context just means will occur without any outside intervention. After watching this video, you should be able to compare and contrast enthalpy, entropy, and Gibbs free energy. You should be able to relate the change in Gibbs free energy to the change in entropy of the universe, and you should be able to calculate the change in Gibbs free energy multiple ways. So we've seen that we can think about the universe as composed of a system and surroundings. The only thing that can go between system and surroundings is heat and work. We're defining the system as a closed system. And so the change in entropy of the universe is equal to the change in entropy of the system plus the change in entropy of the surroundings. Now, the delta S of the system and change in entropy of the surroundings are both positive, then the change in entropy of the universe is also being positive and the process will be spontaneous. If the change in entropy of the system and surroundings are both negative, then the change in entropy of the universe is also going to be negative and the process would be non-spontaneous. It will not occur without any outside intervention. If the change in entropy of the system is positive and the change in entropy of the surroundings is negative, then we do not know the sign of the change in entropy of the universe. It will depend on temperature. And so we also saw that the change in entropy of the surroundings is equal to minus delta H over T. Remember, because the only thing that transfers between system and surroundings is heat and work, the only thing that can affect the entropy of the surroundings is heat. If delta H is positive, it means heat's going from the surroundings to the system, and that would cause the delta S of the surroundings to be negative. And so we can write to change entropy of the universe is equal to delta S of the system minus delta H over T. And so if delta H is positive, that corresponds to an endothermic process. And so heat's going from the surroundings to the system. And so delta S of the surroundings would be negative. If delta H is negative, that means that's an exothermic process. Heat's going from the system to surroundings, and that would cause the entropy of the surroundings to increase. If something gains heat, its entropy increases. And so if delta H is negative, again, that would correspond to delta S of surroundings is positive. And if delta system is positive, then the delta S of the universe would be positive, and that would be a spontaneous process. If delta H is positive, that means it's endothermic. The surroundings is losing heat, so the delta S of surroundings would be negative. If delta S of the system is also negative, that means delta S universe would have to be negative, and that would be non-spontaneous. Now, if delta H and delta S have the same sign, I should mention delta H is always of the system. For entropy, you have to be careful and watch. Are we talking about the system, the universe, or the surroundings? But delta H is always for the system. So if the change in entropy of the system and the change in enthalpy of the system have the same sign, then because that negative sign, we can't be sure about the sign of delta S of the universe. It will actually depend on temperature, whether or not spontaneous or non-spontaneous. And so if we take this equation, delta S universe equals delta S system minus delta H over T, and we multiply through by minus T, we get this. Now we can define the minus T delta S universe as equal to delta G. Delta G is the change in Gibbs free energy. And so it's kind of cool. If you think about the second law of thermodynamics, it's very powerful. It tells you that if the entropy universe would increase, that means the process is spontaneous. It will occur. The hard part is how do you actually calculate the change in entropy of the universe? And then by defining the universe as composed of system and its surroundings, we're actually able to determine the delta S of the universe in terms of the system. Now, through this little manipulation, we're talking about delta G again, this is of the system, and delta G is important. It's a form of chemical potential energy. So think about Gibbs free energy like chemical potential energy. The higher the potential energy, the less stable. The lower the potential energy, the more stable. And so here our reactants are on the left, the products are on the right. And so our delta G is little minus big, so that gives you delta G is negative. Because delta G is minus T delta S universe, negative delta G corresponds to positive delta S universe. And so this would be a spontaneous process. The reactants are higher energy, less stable than the products. Now here the reactants are lower energy, more stable than the products. And so our delta G is positive, products minus reactants. Because of that negative sign, delta S universe is negative. And so this would be a non-spontaneous process. Boulders do not roll up hills, they just roll down hills. And so we have delta G less than 0 corresponds to spontaneous. Delta G greater than 0 corresponds to non-spontaneous. Delta G equal to 0 corresponds to reversible. So spontaneous processes are those that increase the entropy of the universe. They occur without any outside intervention. Non-spontaneous processes are those that decrease the entropy of the universe. They do not occur without any outside intervention. Reversible processes are those that do not change the entropy of the universe. In any spontaneous process, the path between reactants and products is irreversible. A process is spontaneous in one direction is not spontaneous in another. And so again, boulders roll down a hill. They do not spontaneously roll up a hill. You know, the eggs dropping and breaking, that is a spontaneous process. The eggs reassembling and going back in the hand, that is a non-spontaneous process. We can think about here we have a gas in one side of this container. Now, if we open this valve, then the gas will be distributed.
Consider a pair of flasks, one containing gas molecules, the other completely empty. If the flasks are connected at their mouths, gas in the filled flask will move spontaneously to the empty flask by its molecular motions. Eventually, the distribution of molecules will be even throughout the flasks. The final state, in which the matter is more dispersed, is much more probable than the initial undispersed state.
And so opening the valve and the particles being distributed is increasing the number of configurations, it's increasing the entropy of the universe, and that would be a spontaneous process. You know, this is another picture. So here we have the gas in this tube. There's a valve. This is in vacuum. If we open the valve, the gas gets distributed, increasing the entropy of the universe. And so going from left to right is a spontaneous process. Going from right to left is a non-spontaneous process. Gases do not all of a sudden accumulate in just one side of the container. And so delta G greater than 0 would be a non-spontaneous because the products would be higher potential energy. Delta G less than 0 is spontaneous because the products have lower potential energy. Delta G equals 0 corresponds to reversible. And so we can relate delta G to delta S of the universe. Delta G equals minus D delta S of universe. We can also relate delta G to delta H and of the system and delta S of the system. So delta G equals delta H minus T delta S. And so if we look at these numbers, here we have delta H negative, delta S positive, and so that would be negative. Delta S is positive, but you have that negative sign in front, so you have a negative, and that means delta G would be negative. And so if delta G is negative, that corresponds to spontaneous process. Here delta H is positive. Delta S is negative, but you have a negative sign, so this term would be positive, this term is positive, and so delta G would be positive, and so that would be a non-spontaneous process. Now here we got delta H is positive, delta S is positive. And so whenever delta H and delta S have the same sign, whether or not the reaction is spontaneous depends on temperature. And so we got 100 for delta H, we got 2 for delta S, but 2 times 40 gives us 80, so 100 minus 80 gives us 20, and that would be a non-spontaneous process. Now here we got 100, 2, but temperature is 100, so 2 times 100 gives us minus 200, so 100 minus 200 gives us minus 100, and so that means that would be spontaneous. Remember, delta G negative corresponds to spontaneous. So for this process, with delta H at 100, delta S at 2, at lower temperatures, it's non-spontaneous. At higher temperatures, it is spontaneous. If we have minus 100 for delta H, minus 2, again, if delta H and delta S have the same sign, whether or not the reaction is spontaneous depends on temperature. And so minus 2 times 40 gives you minus 80. That negative sign, so that gives you 80 minus 100. And so that gives you minus 20. And so that would give you a spontaneous process. Here we have minus 100, minus 2. This time temperature is 100, so that gives you minus 200. But that negative sign, and so that gives you delta G of 100. And so that would be non-spontaneous. So for the one on top, delta H and delta S are both positive. That means that at high temperature, it's going to be spontaneous. When both delta H and delta S are negative, that means at low temperature, it's going to be spontaneous. And so whenever delta H and delta S have the same sign, there's going to be a transition temperature where the system goes from being spontaneous to go to non-spontaneous. And so if both delta H and delta S are positive, the reaction is spontaneous at high temperature. If they're both negative, the reaction is spontaneous at a low temperature. And so there's 4 possibilities. Delta H and delta S can have the same sign. And so if they're both negative, it depends on temperature. Both positive. Well, if it's the same sign, then it both depends on temperature. If delta H is negative, delta S is positive, it's spontaneous. Delta H positive, delta S negative, it's non-spontaneous. So the following reaction is exothermic. Is it spontaneous or non-spontaneous? And so exothermic means heat's going from the system to the surroundings. So delta S of the surroundings increases. Now for delta S of the system, we have 2 gas particles reactant, 3 gas particles products. So delta system is also positive, and so that means this reaction should be spontaneous. Remember, for all exothermic processes, delta S of the surroundings is positive. And often you can tell if a reaction is spontaneous, you can tell if a reaction delta S system is positive or negative just by counting the number of gas particles. So for this reaction, delta S system is positive, delta S surrounding is positive, so that means delta S universe is positive, and the reaction would be spontaneous. We can also look at delta G. So delta H is negative, delta S is positive, so that means delta G has to be negative. So we just determined that this reaction is spontaneous. Now, if we look at this reaction, we took the products, wrote them as reactants, reactants wrote them as products. And so if you reverse a reaction, if the initial one's spontaneous, the reverse one should be non-spontaneous. If you look at the delta G value, the delta G value should be the negative of the other one. All right, so if this reaction has a delta G, after reversing, the delta G will change the sign. It's actually true for both delta G, delta H, and delta S, that if you switch a reaction, products, reactants, you change the sign for delta H, delta S, and delta G, because they're all products minus reactants. So is the following spontaneous or non-spontaneous? So we're going from H2O liquid to H2O gas. And so if we think about the system, Whenever you go from liquid to gas, you have to add heat, and so this would be an endothermic process, and so that means delta S of the surroundings would be negative. Now, in terms of the system, the entropy of the gas is always greater than liquid, it's always greater than solid, and so delta S of the system is greater than 0. So we have delta H positive, delta S positive. Whenever delta S and delta H have the same sign, whether or not it's spontaneous or non-spontaneous depends on temperature. And so if we look at this reaction, obviously above 100 degrees Celsius, this is going to be spontaneous. Below 100 degrees Celsius, that's going to be non-spontaneous. At 100 degrees Celsius, it's going to be reversible. So change in free energy equals the maximum amount of work that can be done by the system on its surroundings in a spontaneous process at constant temperature and pressure. It is the portion of energy change of a spontaneous reaction that is free to do useful work, hence the term free energy. For delta G greater than 0, the free energy change is the minimum amount of work that must be done to cause a process to occur. And so we can think about delta G in terms of processes. We can also think about delta G in terms of compounds. Now, we cannot determine Gibbs free energy in absolute terms, and so we define elements in our standard state as having 0 Gibbs free energy, and then we measure everything relative to it. But the more negative the Gibbs free energy, the lower the energy, the more stable. The higher the Gibbs free energy, the less stable. And this is relative to elements in their standard state. And so there's tables of Gibbs free energies. There are Gibbs free energy of formation. That's what the F stands for. That little circle on top corresponds to standard conditions. Now again, for elements in their standard state, Gibbs free energy of formation is equal to 0, and all other Gibbs free energies are measured relative to elements in their standard state. And so we measure elements in their standard state going to 1 mole of the compound of interest, and that's actually how we get these numbers. And so if we think about C2H2, it's composed of carbon. Carbon in its element state is graphite. Hydrogen is H2 gas. And so we do this reaction, we measure our delta G, and that's going to be the Gibbs free energy of formation for C2H2 gas. C2H4, again, carbon's graphite, you have hydrogen gas. Now you always have to make sure everything's balanced, which means that you have the same number and type of atoms on either side. C2H6, etc. So the more negative the Gibbs free energy, the more stable the compound relative to its constituent elements in their standard state. So on the compounds in the table, which is the most stable relative to its constituent elements in the standard state? And so that would just be the most negative, and so that would be the calcium carbonate. So enthalpy we saw as kind of a measure of heat content. The best way to think about enthalpy is in terms of change in enthalpy is actually equal to heat transferred to the system under constant pressure and assuming only expansion work. Entropy is a measure of possible number of configurations. Remember, S equals K natural log W. Gibbs free energy is a measure of chemical potential energy. And again, if there's no subscript here, remember it's for the system. So enthalpy is typically always for the system. Entropy we talked about in terms of system surroundings and universe. Gibbs free energy is also for the system. The enthalpy and Gibbs free energy of a compound cannot be determined in absolute terms, so they're determined relative to elements in their standard states having 0 enthalpy and Gibbs free energy. Entropy can be determined in absolute terms. Remember, the third law of thermodynamics says that a perfect crystal at 0 Kelvin has 0 entropy. And so if we look at tables of numbers, these are all elements in their standard state. And so they have 0 enthalpy of formation, 0 Gibbs free energy of formation. But again, the entropy is non-zero. Third law says that perfect crystal at 0 Kelvin has 0 entropy. Again, these are noble gases. These are elements in their standard state. So 0 enthalpy, 0 Gibbs free energy. These are metals. They're just going to be solids. So these are elements in their center state. 0 enthalpy of formation, 0 Gibbs free energy of formation. And these are transition metals. And so this is just going to be solids by themselves. And that's how you recognize that they have their elements in their center state and will have 0 enthalpy of formation, 0 Gibbs free energy of formation. Now for these, that I just couldn't find entropy terms for, like scandium, and that's why these are blank. And so this is a periodic table that indicates the center states for the elements. And so the reds correspond to solids, the yellows correspond to gases, and the blues correspond to liquids. And so the only really 2 elements are known to be liquids in their center state would be bromine and mercury. Now again, remember, like oxygen is going to be O2, so you have that 2 there, nitrogen's N2, fluorine's F2, chlorine's Cl2, bromine's Br2. Now all 3 of these are state functions, and so we can find the change by doing products minus reactants. And so delta H is the heat amount absorbed by the system. Delta S is a measure of the change in number of configurations. And minus delta G is the maximum amount of work that can be done by the system. You can also use delta H again to get the delta S of the surroundings. So delta S surroundings equals minus delta H over T. Delta system is equal to products minus reactants for the entropies. And again, remember delta G is minus T delta S universe. And so we can calculate the change in Gibbs free energy for a reaction. That's why they are there, by just doing the products minus reactants thing. Remember, you can do this for change in Gibbs free energy, change in enthalpy, and change in entropy. And so if we look at a reaction, remember the stuff on the right is always going to be products. Stuff on the left is always going to be reactants. And so products minus reactants. So we have carbon dioxide. Remember the 2 here comes down, so 2 times the Gibbs free energy formation of H2O gas minus Gibbs free energy for the methane plus 2 times the enthalpy formation of O2. And so you multiply the G times the coefficient. If we plug in the numbers, we get delta G equals minus 801 kilojoules per mole. And so that means that this is a spontaneous process. Remember, delta G negative corresponds to delta S universe positive, corresponds to a spontaneous process. Also, I should mention that notice that O2 is the element's center state, and so it has 0 Gibbs free energy of formation. And so you could be asked this question: is the following reaction spontaneous or non-spontaneous? And so again, what we're going to have to do is calculate our delta G for the reaction. So products minus reactants. So we got CO2, which minus 394, minus, that's element center state, so 0 plus 0. And so that gives us, for this reaction, a delta G of minus 394. And so that would be a spontaneous process. And so we can think about it if we plotted the free energy on the y-axis, and here we have reactants and products. The products are lower in energy, more stable, and so this reaction is going to be spontaneous. And so there's 3 ways of actually calculating delta G. We can use delta G equals delta H minus T delta S. We can do delta G equals products minus reactants. And remember, we define delta G as equal to minus T delta S of the universe. I hope that was helpful.